Okay, guys, the last concept that we need to cover in our functions and relations unit is the concept of inverses. So we're going to do this concept over two separate videos, so that way they're a little bit shorter each. So there's three things I need you to know about inverse. So I need you to know how to graph the inverse of a function. I need you to know how to find the equation of the inverse of a function. And I need you to know how to figure out the domain and range and how they are affected by the inverse of a function. So whenever you see the word inverse, I want you to think switch. We're going to switch the x and y points. We're going to switch the x and y variables. And since domain is x and range is y, then we're also going to switch that as well. So this is our sixth operation. What it looks like is this. So if y equals f of x is our original function, this is our original. The way we show inverse is to write f to the power of -1 of x or x equals fy. So typically in questions, it won't say determine the inverse of the following. It will just say find x equals f of y or find y equals f to the -1x. So you have to know that that means inverse. Okay, so looking at this first example here, it says consider the function defined by the following set of ordered pairs. So I'm just going to go ahead and graph these points on here. So -4 comma -2, -2 comma -1, -1 comma 0, 0 comma 1, 2 comma 4, and 3 comma 8. Okay, so if I'm just going to, and I'm just going to connect them just with a smooth curve. So that's my original. I'm going to call that f of x. So describe the inverse of the function as a set of ordered pairs. So remember, inverse means to switch. So it means to switch the x's and y's around. So my new set of points would be -2 comma -4, -1 comma -2, 0 comma -1, 1 comma 0. So you don't switch the signs, you just switch the position of the numbers. Now I'm going to plot those on there as well. So -2 comma -4, -1 comma -2, 0 comma -1, 1 comma 0, 4 comma 2, and 8 comma 3. And I'm going to connect those ones. And I'm going to call this one f to the -1 of x to show that that is the inverse. So part C says draw a line which acts as a mirror line between the original function and its inverse. So what this is asking is, what is the reflection line? So where would you bend your paper? So if you could cut this out and put it on a piece of paper and bend that piece of paper, where would that reflection line be in order for the blue graph to lie directly on top of the red graph? And where it happens to be is it happens to go through pairs of points. So 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, -1, -1, -2, -2, -3, -3, and so on. So if I put this as a dotted line, that is referred to as my mirror line. Or in other words, if I were to reflect, or if I were to flip the blue line over that, it would lie exactly on the red line. The mirror line has the equation y equals x. Now the reason why this is the mirror line is when y equals x, so let's say 2 equals 2. Well, let's say the point 2 comma 2, and let's say you did the inverse of 2 comma 2. What would the inverse of 2 comma 2 be? 2 comma 2, right? It doesn't change, it doesn't move around. So mirror line is that line because even if you flip the points, they never move. Okay, so that is your mirror line. So I hope you can visually see that if I were to flip my blue line across my green line, it would lie directly on the red. Okay, so to determine the inverse of a function defined by a graph, reflect the graph of the function in the line y equals x. So again, this is your mirror line. Alternatively, select the coordinates of some key points, interchange those points, and plot the new. So what this is referring to is Our original is x comma y. We're going to do the inverse, and we're going to flip those points around. Okay? So we can use those two ideas to graph an inverse. So let's start here. So this is my original graph. Notice that the scale is everything's counting by twos. So right here, it's negative 6 comma 0. So my new point is going to be at 0 comma negative 6 right here. So this point got moved to here. 0 comma negative 6 becomes negative 6 comma 0. So that point got moved to there. 6 comma 0 is going to get moved to 0 comma 6. So this, the blue graph, is my inverse. Okay. Now, if I sketch the mirror line in, so going all the way through, it's a 45-degree angle. Now, I'm going to do this with my erasable ink. So I want you to be able to see that, so this is the original graph. So the original graph went like this. Okay, so that's the original black graph. So that line, that graph right there, when it's reflected, it becomes this right here. Okay. Now, the original is this. When that gets reflected, it became that. So if I put this part together with this part, that's how I get that inverse image. So by drawing the mirror line in, we want you to be able to visualize those points. We want it to look like, yeah, if I took that black graph and flipped it over that green line, I would end up at my blue line. So same thing here on this one. So again, it's counting by twos. So negative 6 comma 0 becomes 0 comma negative 6. 0 comma 4 will become 4 comma 0. And 6 comma 0 will become 0 comma 6. Now notice we're not changing the shape of the graph, we're just changing where it is drawn. So again, if I just draw in my mirror line, and if I just use my erasable pen, so it's just not quite drawn perfectly, but essentially this part right here is becoming this part right here. And then this part right here is becoming this part right here. Okay, so I just didn't do a very good job of drawing that. But again, if you flip those points around, it should visually look like it should look like it's been reflected across that line. It should make sense. Okay, so that's how you do the graphing. You just take the points, flip them around, replot them, and then if you draw the mirror line in, it should look like it's been flipped over that line. Okay, so to find the equation of an inverse, what you do, again, keyword is switch. So instead of switching the x and y coordinates around, I'm going to switch the x and y letters around. So it says find an equation in the form y equals mx plus b. And this is my original, y equals 3x plus 2. So my original is y equals 3x plus 2. So for inverse, what I'm going to do is I'm going to switch my x and y coordinates around. So I'm going to have x equals 3y plus 2. Now I have to get the new y by itself. So basic algebra here, we're going to subtract 2 from both sides. And then I'm going to divide both sides by 3. Now there's nothing wrong with leaving the answer like that. That is a perfectly good way of doing it. And by the way, to show its inverse, we just put to the power of negative 1. Another way to write the equation, though, is to understand that this is like saying 1x minus 2 over 3. Whoops. And because I have 2 terms in the numerator and 1 term in the denominator, I can actually separate this up to write it as 1/3 x minus 2/3. And now that's that m and b equation from grade 10. Remember, mx plus b, m is the slope, b is the y-intercept. So if I would use my calculator, that's the other way you could do this. So if you plug the original into y1 on your calculator, you would have a point at 0, 2, 1, 5, negative 1, negative 1. Those would be your originals. Okay, so this is the original equation. So you can label it f of x, you can label it y, you can label it original. Now, I could then plug this into my equation, into my calculator, and plot another 3 points. Or what I could do is I could use what I just learned about graphing. So if this point's at -1, -1, if I flip those coordinates around, I'm still at -1, -1. 0, 2 will become 2, 0, and 1, 5 will become 5, 1. So that is my inverse. Now if I draw in my reflection line, you should be able to see that the blue, so this part of the graph, so this gets reflected over and becomes that, and this gets reflected over and becomes that. So again, you can use your calculator, you can use manual, you can do whatever. I do want to talk about this point right here. So this point on the original was -1, -1. When I flip those points around, it stays as -1, -1. So this point did not move. Points that do not move after you've done an inverse, they are referred to as invariant points. If you think about the word variant or vary, things that vary are things that change over time. So things that are invariant are things that don't change over time. So AKA they don't move. Okay, so any points that don't move are considered to be invariant. Okay. So there is something called the horizontal line test. So in grade 10, I taught you about the vertical line test, and that's how we use to determine if something is a function or not. Now, there's also something called the horizontal line test. We can use it to determine if the resulting inverse image will be a function or not without having to graph it first. Okay, now this is where the reason why I cover this is mainly for the diploma. The diploma is always written with perfect math language. So if a graph is an inverse, after you've done the inverse on a graph, if that resulting graph is a function, it's shown with f to the power -1 of x. If that resulting graph is not a function, it's shown with y to the -1. Now, for some kids, that trips them up. They're like, why are you using f -1 here, but y -1 there? I don't get it. And the reason is because it's a function or not a function. Okay? So here's how this horizontal line thing works. If you put a horizontal line onto the original image, if it intersects that graph in more than one spot, anywhere on the graph, then the resulting inverse will not be a function. Okay? So let's put this to use. So here's my original. So is my original graph, so this is f, this is some graph, is it a function? Well, if I take a vertical line across my original graph, so this is what we did in grade 10. Does my vertical line only ever cross it once? Yes. So is my original graph a function? Yes. My original graph is a function, so I'm going to label it with f of x. Okay. Now, would the inverse graph be a function? So could you go ahead and draw the inverse of this? Yes. And I will show you how to do that in a minute. But if you were just asked, if that was the only question, would the inverse of this graph be a function, yes or no? Here's how you can do it. What you would do is you take a horizontal line. So here a horizontal line crosses the graph once. Here the horizontal line crosses it once. Here a horizontal line crosses it a bunch of times. Here a horizontal line would cross it a bunch of times. So because the horizontal line is crossing the original graph more than once, then the inverse will not be a function. Now, just to prove this to you, let's just go ahead and flip the points around. So this one right here, 1, 2, 3, 4, 5, this is at -6, 4. So at 4, -6, we would have that point. And then here we have the point -4, 6. So at 6, -4, we're going to have a point. And then here at 0, 6, so at 6, 0, and I'm just going to connect the points as I go. 2, 2, so 2, 2 is going to stay. Remember, that's going to be an invariant point. 4, 2 is going to become 2, 4. And 6, 0 is going to become 0, 6. So here is my inverse. Now, if I were to take a vertical line across my inverse graph, see how my vertical line crosses that graph more than once. So then I can say that my inverse is not a function. So the way I would show it, I would say it's y to the -1. I wouldn't use f to the -1. Okay? So horizontal line test is merely for just notation. So you just want to always make sure that you're notating it properly. Now again, if we were to draw that reflection line in, remember this is the invariant point right there because it didn't move. Okay, and hopefully you can see that this part of the original is now been reflected over here. Okay, and then hopefully you can then see this part of the original has been reflected over there. Okay, so this is the end of the first video on inverse. The assignment will be attached to the end of the video, so do make sure and look for that. And as always, if you need any help, don't be afraid to ask.